Alright, today we're looking at reduction formulae, which is the last little thing in this topic. So, we're going to start with something looking a bit like this. Now, what this means is it's a sequence of integrals defined where in equals the integral of xn e to the x dx. So, say I1 would be x to the power of 1, ex dx, so that's with n equals 1. I2 would be with x squared instead, so n equals 2. I3 would be with x cubed with n equals 3, and so on. The idea is to work out some sort of relationship between these in, often by using integration by parts. Not always though, we'll see an example of that. And we use this relationship to reduce the value of n if we're asked to work out something like, say, I3 or I4. We can use this relationship between them, if we can see one, to reduce the value of n. Alright, and that gives you hopefully an easier integral to work with. Okay, and we'll use this one as an example, so let's try and integrate this one. Again, the idea is to first work out some relationship between an in and maybe a smaller value of n, so say n minus 1 or something like that. Alright, so we integrate this by parts with the intention of maybe reducing the value of n. So we're going to choose to differentiate xn and integrate ex. Not only is that easier, but when you differentiate x to the power of n, you get an x to the power of n minus 1. So that's kind of promising, because that might end up being the integral, but with the n minus 1 in the power instead of n, which would reduce it to a smaller term in the sequence. Okay, and we integrate ex, nothing happens, of course, so integration by parts, the in becomes this thing, and as we expected, the integral we end up with is exactly the same as what we started with, except the power of n has dropped by 1. So this integral is actually in minus 1, and this is the relationship we've got there. Okay, and so knowing this now, we can work out the integral for larger values of n by reducing it to smaller values of n, which could be easier to work with. Right? Now, in practice, how we often do this is, rather than go that way, I think it's easier to actually go in reverse. Right? So you build it from the ground up. Okay, and the easiest ground to start with for this one is that, well, this works for I0 even. That's the easiest one, I think, to work with. That's where the power of x is 0, and that's just 1. So it's just the integral of ex, which is, again, just ex. All right. And so from there, we can work out all the other ones. So say I1 would be, using the green box, x to the power of 1 ex minus 1 I0. Right, and so we would get this thing, right, because I0 is just ex plus c. Now you might be wondering why I haven't put a minus c there, because it should be minus ex minus c if you expand it. I'm going to be a little bit relaxed with how I use that letter c. It's going to stand for any constant. And so, yeah, it should be minus c, but that's just a constant anyway, so I'll go plus c, alright? You'll see why that's important soon, because otherwise there's going to be a lot of constants to deal with. Okay, so if it's constant, I'll just say plus c. Alright, so using this one, we can work out I2. Using the green box again, I2 should be x squared ex minus 2 I1. Okay, now this time I put all of I1 in the pink in brackets, and so we get this thing. We expand, but again, I won't write minus 2c, I'll just write some constant c, because that's what it is. Okay, and that's what we get after expanding. And so I3, if we're looking for that one, again, green box, it would be x to the power of 3 ex minus 3 I2, right? Because it's the one before, and so we sub that into the I2, expand, and we get this to be the integral of x cubed ex dx. Okay. Alright, sometimes we don't use integration by parts to do this. Sometimes we just use a bit of algebraic manipulation, right? But first we're being asked to calculate I0, so let's do that. Now if it's I0, it means it's x to the power of just 0 up top, which means we have the integral from 0 to 1 of 1 over x squared plus 1 dx. This is one that is a given standard integral. This is an inverse tan. And so from 0 to 1, we just get pi on 4 from that. All right, part B, show that this relationship exists between them. Now, in minus 1 is a thing that we don't really know about here, so let's try and work that out. That means that the power of x up top is 2 bracket n minus 1. That becomes 2n minus 2. And from here, what can we do? Now, I don't think any integration by parts will be helpful here because we don't really want tans to appear just yet. And the power is going to decrease in a weird way. You might get 2n minus 3. That might not be very helpful. All right, so maybe this is one we can just sort of trick our way through, right? And the way we do that is, we've seen this trick before. We can plus or minus the same thing up top. Okay, now that one might take a bit of practice to see. But why that's helpful is because we actually can factorize this one, right, by pulling out x to n minus 2. And if we pull out x to the 2n minus 2, we actually get this thing. And that's a very helpful way to split the fraction because the 1 plus x squared up top will cancel the x squared plus 1 down the bottom. And what you're left with the yellow x to the 2n, is exactly what we started with. Okay? And we can integrate x to n minus 2, the pink one. We can integrate very easily. It becomes that. But the important thing is that the integral on the right is exactly what we started with, the in. Okay, and so working that all out, we get in minus 1 equals 1 over 2n minus 1 minus in, right? And that is exactly the thing we were looking for in part B if you just shove the in to the left. Okay, and so that's what we've got from doing that. In practice, though, we might actually use it as in equals 1 over 2n minus 1 minus in minus 1, though. Okay? All right, so part C, find out this one. Well, what this means is that n is 2. All right, so what we're looking for is what's the value of in when n equals 2, because 2 times 2 is 4. Okay, so we'll again build this from ground up. We start with I0. So I0 we worked out previously was pi over 4, right? And so from this we can get I1. Now, again, think of what's up top there. I1 must be 1 over 2 times 1 minus 1. Take away I0. If you move the in minus 1 to the other side. And so we get 1 minus pi on 4. And so again, using that relationship up top, I2 must be 1 over 2 times 2 minus 1. Take away the previous, so I1. And so we get 1/3 minus 1 minus pi on 4, which simplifies to pi on 4 minus 2/3. Okay, and so that's reduction formulae. Thanks for watching, and I'll see you later.